Well, g'day. Iron Horse here, and been wanting to make a video for some time now to try and describe some of the things that see if I can get my hair out of my face a bit. Some of the things that we've been having difficulty with in understanding some of the concepts that people struggle with about the flat Earth. How do you like my new place? Hey, it's pretty cool. Still moving in, so it's going to be a while. I'll get the bed happening one day. So the thing that needs to be discussed, I think, is this line, because it's clearly above the sun. It's a picture I've had for many years. The glass is actually cracked on it. Could be cracked. I can never do this in reverse through the glass there, but it's still a cool picture. I'll probably end up taking the glass off it actually, and it would have less reflections of the kitchen window. Good idea. But until then, clearly we can see this lion is above the sun. He's bigger than the sun. The sun is tiny and low, because seriously, this is part of the globe mentality. Now hear me out here, because I'm going to have to put this down. I think it's getting a bit... there we go. Right here. The global mentality is that the sun goes below the horizon. Now, picture this, if you will, or go outside and go and watch the sunset or watch the sunrise. You most likely will want to go to a very high place, like a mountain, somewhere with a good lookout. Now you know why that is, because on the flat Earth, getting higher allows you to see further. Now the glober will tell you that getting higher lets you see over the curve. Seriously, this is what they think. Like, they haven't put two and two together to realise that above a flat surface, the higher you get, the greater your angle of elevation, so the further you will see. But if it was curved, if it was curvature creating your horizon, going higher will not give you the ability to see further. All it will do is show how much less you can see as the horizon drops below you, because you are in fact going backwards away from the distant curvature if you're going up. This is how it works. Up, of course, opposite of down. Down is towards the center of the ball. So up, away from the center, means on a curve, you know, let's say we got 90 degrees out there and 90 degrees up there, with a curve, and going up, up is going away from the curve. It just has to be. Like, just stick some pins in a ball or some long skewers through an orange, and you'll see that the tops of the skewers get further and further away the further out or up they go. That is just natural laws, basic geometry of shapes, of a circle, of a ball. So going up on a globe, well, to a certain degree, will allow you to see further. After a certain point where the curvature drops, takes it away what you can see, which on the sphere of 25,000 miles circumference, or 40,000 kilometers, depending which measurement you'd like to use. I'll stick with miles. 25,000, it's a little bit less. It's about 24,930 or something ridiculous, but 25,000 miles, right? After 3 miles, if you're standing at sea level, looking out across the curve, then at 3 miles, that is where the horizon will have dropped 6 feet. And it's still at eye level, absolutely perfectly at eye level, but according to spherical geometry, it is at foot level. So any further beyond that, you not only have to go up, but you have to go forwards over the curve to see what's on the other side of it. That's how curvature works. It's like if you look at a mountain in the distance. A mountain is a true example of curvature because obviously the land is no longer flat. It curves up and down the other side. And so if something climbs up the mountain, goes over the other side of the mountain, it doesn't matter. Oh well, eventually, if you got really, 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 really high, but it doesn't matter how high you go, you will not see the person on the other side of the mountain until you're really, really, really high. Unless you go forwards and over the curvature of the mountain yourself to see what's on the other side again. It's very, very, very simple. So when they say the sun is setting below the horizon, they are saying that the earth is spinning towards the east to give the illusion of the sun setting in the west to go below the horizon. But your horizon is 3 measly miles away. 3. That's like nothing. You can walk that in less than an hour. How can the sun be going beneath something 3 miles away when the earth, with a 25,000 mile circumference, must have, okay, sun overhead means it's lighting 6,250 miles that way, 6,250 miles that way, so that by the time it sets, it must be over 6,250 miles of Earth curving away, which is the equivalent of 4,000 miles of drop, curvature drop, because you've got your sphere, divide that into 4 sections, right? The core in the center, every direction away from the core is 4,000 miles. So if the sun is covering half the Earth at a time, then there's 4,000 miles of drop there and 4,000 miles of drop there when the sun is overhead. So when the sun sets or rises, it's 4,000 miles of drop away and 6,250 miles distance of Earth's curvature. So you cannot see the sun through your tiny, tiny, tiny little window of opportunity where your horizon is just 3 miles away when it's 6,250 miles away either side over 4,000 miles of drop. And not only that, when we see the sun go below the horizon, you can stand up or walk up a hill and see the sun again. You can get a drone. You can send a drone up higher and higher and higher and watch the sun set again and again and again. Now, on the sphere, globe, spinning ball, hurtling through space at 1,040 miles per hour around the equator, that's how fast it's spinning, which is really, really slow because it's once every 24 hours, but you get that out the size of the Earth. The land speed of the surface is going faster than the speed of sound, 767 miles per hour, the speed of sound. We're moving towards the east on our axis. Forget the orbital spin for the moment. This is just on our axial spin. 1.35 times the speed of sound, like Mach 1.3 and a half. It's ridiculous. Actually, it's not and a half. It's 1.35. It's 1 1/3 times the speed of sound. It's a crazy, ridiculous speed. So, if that is the case, and you send a drone up, which is, as we've already discussed, away Plus it's going with the atmosphere of the Earth, don't forget, because the atmosphere moves 1.35 Mach plus those little increments as you get further and further up. It's also going that little bit faster and faster and faster to create the illusion of being perfectly still. So the drone going away from the setting sun with the spin of the Earth sees the sun over 4,000 miles of drop, 6,250 miles away, just by getting a little bit higher and higher and higher. It can't work. The only way it's possible is if that drone was flying faster than the speed of sound, faster than the spin of the Earth, towards the west, which no drone, not one of our little buzzy handmade or hand-controlled drones could possibly do. Maybe a military drone would be possible to go that fast. Something like a fighter jet can go that fast, but commercial airliners only go half that speed or a third of that speed. It has to go that fast towards the west to see over the curve like you would over a mountain, because curve is real. You can't just get higher and it magically flattens out, because that is exactly what the globe heads believe is happening, just to see the horizon. I was looking at one today, a guy showing a picture of a boat, or no, let's not use the boat. This is on metal bunk. It's so he showed a picture of a hotel across the water, and it's partially hidden by the water, and all he had to do was stand up and take another picture, and you can see it. So that proves the Earth's curve, and yet you can never see it left to right. But where did the curve go? But just because you get up higher does not mean the curve that was there magically vanishes into thin air, and yet the globers just accept it. Oh, we got above the curve, and so therefore it's disappeared. But, you know, if you're looking at a mountain, again, a real example of curvature, just getting up higher doesn't make the mountain look flat. It doesn't make the mountain look flat. And yet when you look at curvature across water, you believe that getting up higher will flatten out the curve. Oh yeah, we're flattening the curve now, aren't we? Because what you don't understand is this simple aspect of perspective. You can even see it in that window behind me here. See how that one's going like that, and this one's a bit flatter, then this one's a bit flatter again, and now this one's at eye level, and now this one's starting to go down. Convergence and perspective are real facts of life wherever you go, whether you've got parallel lines to show it for you or there is no lines to show it for you. Convergence is a very real thing, and that one at eye level is always going to be at eye level. So if I'm not even going to bother doing that. It's silly. That's about eye level. We don't need to move the camera up and down to show, because I've done that before on my Perspectives video playlist, where you can see the brick wall. As you move up and down the brick wall, the one line that stays horizontal is always at the camera level or at the eye level, depending on what's viewing it, and it will always be the case. You will always have the parallel line at eye level, and everything out beneath converges up to that, everything above converges down to that, and creates a convergence point. So depending on your viewing height, especially when you're looking across a vast distance like a large lake or body of water, then the water will be ramping up to eye level and create a convergence point, from which point everything taller than that will be cut off from the bottom, but you can still see the tops of it because it's not cut off, and all you have to do is get up higher and you see further and you see more of what was hidden by convergence. So anybody who mistakes that as curvature is a brainless fool. There's no excuse anymore to believe it's curvature when it's convergence. There's no excuse unless you're just mentally incapable of understanding simple logic. So now I'm going to go one step further, because I was asked to in my last video to say more, because somebody requested I describe the moon. So unless you understand the nature of light in the first place, like it's very overcast, quite foggy, and not at all sunny at the moment, a lot of rain. We're actually getting more floods down in Sydney area and moving north towards where I am, so hopefully we won't get more floods. The nature of light is such that the sun is an energy source. What the source of the sun is, I do not know. What we do know is that we can see it when we send up high altitude cameras up on helium balloons, is through this lens of the firmament, which I believe to be 60 to 70 miles high above the Earth, which if you look at a normal diagram as we see on our computer screens or on our phones, we see a picture of the flat Earth and we see this big dome. Well, that's not how it would actually look to scale. To scale above a flat Earth, the dome would even be a pixel high. If we're going to represent the Earth this big, the Earth is massive, okay? So it's 25,000 miles just around the equator. That's the equatorial measurement. That's not the globe measurement, that's just the equator of the flat Earth. So it's probably 80,000 miles or more around Antarctica. We don't exactly know. We know that Captain Cook charted at least 60,000 miles over a period of 3 years, failing to find a way through to the promised Great Southern Land, which is a story for another day. All we know is the Earth is massive. The sun goes around the equator and it circles, and I'll get back to the firmament first, because the firmament, being 60 to 70 miles high, is like nothing at scale. It's tiny, but to us, it's massive. You know, a plane flying at 5 or 6 miles high becomes a tiny dot. We can barely see it. When planes go above 12 to 14 miles high, what I will call firmament B, the sky goes from blue to black, and that's when they think they've hit the edge of space. 12 to 14 miles. So the firmament at 70 miles is massive. Yeah. Burj Khalifa, world's tallest building, half a mile. Massive. So 60 to 70 miles high is massive. But when we're looking at models, because everybody wants to see the model of the flat Earth, the model, the firmament is a pixel high, 2 pixels at the most. So you can't model it. It's too big. So the firmament B, 12 to 14 miles high, that's where the noble gases are that fluoresce to give us daylight. And at the 60 to 70 mile height of the firmament, when we get above the firmament B, we see the sun. We see a hotspot apparition through the firmament. Now the sun itself is probably 3,000 to 4,000 miles high above that, so massively far away. Directs energy into the firmament. That energy radiates down and illuminates the noble gases in a direct line of sight to create daylight. So it's almost as though it would be like a laser light shining into the firmament. And because we're seeing it now through firmament B, it makes the sun look much nearer and closer, and it rounds off the edges to make it look like a clear, a circular orb without the sun rays coming off in every direction, the crown of thorns that you do see when you look at the sun through the firmament, or when we see it through videos and photography. We can't go up that high ourselves for very long anyway. We can get above the 14-mile height, but again, nothing to breathe up there, no pressure. We rely on air pressure to be able to breathe and circulate blood and not boil and evaporate. We need air pressure. I think I went into that in my last good rant. So the sun that we can't see is just 70 miles high. The sun that we do see is just 12 to 14 miles high. And because we're seeing it through these layers, we see a personal, subjective sun. So somebody 1,000 miles away will be looking through the layer at 1/4 of a pixel, so the layer at 2 pixels high, and seeing a completely different sun in a completely different place from the one that you're seeing. So the sun is everywhere and nowhere at once. So that is why you cannot triangulate a distance to it. Wrapping that around to get back to the moon, I probably should have to describe what the moon is. The moon is an artificially created satellite made here on Earth, probably by giants, melted in a massive furnace, such as Yellowstone National Park volcano, and all the raw ingredients mined from somewhere, perhaps like the Grand Canyon. Blown into a giant bauble in an effort to create a second sun. Recording will be stopped. Oh shit. Go away, fraud. Bloody fraudster's always trying to call me. So, the moon is an artificial satellite, and as it rose, the molten material rapidly set, and as such, bubbles on the surface burst, and as they burst, they set into place, and that's what created the craters. And so this moon is probably about 70 miles wide. It's massive. Maybe it's a lot less, maybe it's a lot smaller, I don't know. But it's at least 70 miles high. And it is a physical thing. And so what it does, being about the same height as the sun, gets illuminated by the sun. Yes, the moon is lit by the sun. That is why you see the shadows in the craters, the shallow craters formed by bubbles. And that moon is like a tiny little star that we see near the moon, we see and call the moon. That's right. The moon that we think is the moon, it's not the moon. It is a plasma projection. And so, for all those people who've been saying all along that the moon produces its own light, it's correct to a degree. It's also wrong to a degree. It's both. It's right and semi-right and sort of wrong. The moon is lit by the sun, and that's when we see that star named the crescent moon. That's actually the moon. A lot of people say it's Neptune or Jupiter or Venus or one of the planets. It's not. When we see high altitude balloon footage, you don't see the moon. Sometimes you'll catch a glimpse of this tiny little thing, like it'll be a golf ball compared to a basketball from the sun to the moon. That's the real moon. It projects, reflects, sends solar energy into firmament B, the gaseous layer of the noble gases, and it affects the layer of gas called krypton. And krypton, one of the noble gases, it's a very trace element, but it's, when you say trace elements, when you're talking about, say, if you've got $200 billion trillion and you're only going to get 1% of it, you're still going to be a millionaire. It's still a lot. So trace doesn't necessarily mean nothing. It's still a lot. And so the krypton glows in the presence of the moon's illumination, not the best word for it, fluorescence from in direct line of sight between the actual moon and the viewer, in most cases, give or take refraction. Now, refraction sometimes does bend light slightly, and that's why sometimes you'll see the star near the moon, and sometimes, if you're really lucky, through the moon, because that's the moon, it's not a star. And so that's why the moon is a plasma projection, holographic plasma projection. So it doesn't matter where on the planar Earth you are looking up towards it, you're going to see the exact same phase, because you're not seeing the moon, you're seeing the holographic projection from the sun onto the moon through the atmosphere to your eyes to create the illusion of the moon. That's why at night it looks like it glows like a lamp, because it is glowing like a lamp. It's a big ball of holographic plasma sitting up there, only 12 to 14 miles away. That's why the moon does look so close, because it is so close. It's not 238,000 miles away in outer space, wrapping around us as we're warping through space at 67,000 miles per hour, going around the sun 514,000 miles per hour. Because we would not have a moon if that was the case. We would leave the moon in our space dust, billions of miles away. It's just not possible. I'll get to tides another time. Well, I've still got a bit of time here. So, the moon going around above us, similar to the sun, takes 24 hours and 50 minutes per cycle. The sun takes 24 hours, exactly. And the sun, as it gets higher, which it just did until June 22nd, my birthday, yeah, you missed it, I'm 51 now, starts to then spiral around every day, getting a degree lower and lower and lower until December 22nd, which is the day, well, they bastardized that belief, didn't they? Because the Son of God is born 3 days after the solstice, because they see the sun rising again 3 days and nights after being in the underworld, and the giver of life returns again. That's the whole Christmas tradition. In the southern hemisphere, it sort of goes the other way. The sun actually reaches the top, and so now the sun is actually returning back to Earth. So, back towards Earth anyway, until December 22nd, and then it actually starts going away again. So, the northern hemispheres, the inner hemispherians also have a bit wrong on their ancient religious beliefs, worshipping the sun, which is what gives us the whole heliocentric tradition in the first place. So anyway, so that's how the seasons work. As the sun gets lower, summer in the south. As the sun gets higher, summer in the north, because the firmament is still the same height above the earth the whole time. So the direct line of sight to the sun creates the most heat, and heat doesn't come from the sun either, it comes from light. And light basically reflecting from things, the earth, and the fluorescing noble gases. That's why once you get a bit higher, it gets colder. The sun isn't hot. So, and nor is the moon. Well, the moon actually itself could be quite hot, because it's quite, well, it's way the hell up there. There's no atmosphere up there. Solar energy hits it, radiates down through the atmosphere, creates the personal apparition, the subjective apparition of the moon. Same phase everywhere, but it will be inverted depending if you're on the inner side of the equator or the outer side of the equator. It's like if you painted a 6 on the floor and you stood on the side of the 6 and somebody stood opposite you, they'd look at it and they'd say it's a 9, and you say no, it's a 6. And you could go back at some points all day arguing that, and then you could spot places and say, oh yeah, it is a 9. And you go, no, it's not, it's actually a 6. That's why it appears inverted from opposite sides of the equator on the stationary planar Earth. So, because the moon takes that 50 minutes longer each day, that's nearly an hour's difference. So you've got the sun on one side of the planar Earth and the moon on the other side of the planar Earth. That's when the fully lit side projects down onto the dark side of the Earth. And it's the only night of the month where you will see the moon all night long is the full moon. The next day, because it's delayed by 50 minutes, it rises an hour later. So say it was 6 o'clock sunset on the night of the full moon. Then the following night it's nearly 7 o'clock before it rises again, and it's well and truly dark. And it's not quite a full moon, it will still look very, very full. And then of course subsequently every day you get less and less, until the point where by the time the sun sets, the moon is only halfway to that point. So it's called a quarter moon. And then by the time the sun sets, or rises, doesn't really matter, that's the sun and the moon are in the same place. And that's when we have a new moon. And occasionally the moon will cross the path of the sun, and that's what gives us a solar eclipse. And then the next day, then the moon is delayed another 50 minutes. And so of an evening, when you look out, you'll see the really thin crescent. And then that crescent will slowly start getting bigger and bigger, and later in the evening, until eventually when it's a half moon again, the next quarter moon, it will be directly overhead at sunset. Yeah. And that's what gives us the phases of the moon. It is lit by the sun, projected into the, I didn't fully explain that, did I? Into the krypton band of noble gases. Now, if you look at noble gases, again, I think I've even got a playlist called Nature of Light. There's some excellent videos on there, not by me. I don't do scientific experiments that well. I think it's Dimension or something like that. Excellent ones where you've got different test tubes of gases, noble gases, and brings them into the stimulus of a Tesla coil. So it's just into an electrical field. There's no power actually connected to them. And as it comes into the electrical field, they start to glow. And krypton glows white. It doesn't have color in it. And you'll notice under moonlight, even if you can read a book under a full moon light, you cannot see color. If you have a colored picture in the book, it'll appear black and white. So moonlight is black and white, and krypton also glows without producing heat. So that is why a lot of people say the moon produces a cool light. Now, it's not a cooling light, it's just a light that has no particular heat. But on a very, very cold night, you will find that because that light is still stimulating some of the other atmospheric gases, that you can feel a very subtle, gentle warmth coming from moonlight. And that subtle, gentle warmth coming from moonlight is what causes something to cool faster in moonlight, because as we know, at night time, heat rises, things cool down. So adding a tiny little accelerant to that effect will make the heat rise even faster, which causes more cool air to rush in to fill the void, and it will cool things faster than something that was left in shade from the moonlight. Now, you will get some globers. This is a crack up. This one has to make you laugh. He'll say, yeah, well, why don't you do it on a night without a moon when there is no moon? It's like, are you seriously that mentally deficient that you think you can test moonlight to moon shade on a night without moonlight? Yeah, they actually do think that. No, you have to do it on the same night, because every night's going to be a different temperature regardless, isn't it? And for those people who still believe in that silly nonsense that flesh will spoil if left out under moonlight, hello, whether there's moonlight or not, if you leave dead flesh out overnight, unrefrigerated, it's going to spoil. It's got nothing to do with the moon's phase. The sun, on the other hand, that light is curing because it has all these UV, sterilization and dehydrating effects. Now, you wouldn't expect that to come from moonlight, which is just reflecting solar energy to create a plasma moon in the atmosphere. You wouldn't expect it to mimic sunlight, or if you do, then you're not fit to be called a flat earther. flat earthers are supposed to be at the forefront of modern day science and understanding. We've got all this technology at our fingertips that the people from thousands of years ago never had, that people from hundreds of years ago never had, that people from 20 years ago never had. The digital camera is the game changer, and we're able to send it up high. We're able to see and gain more understanding about this stationary planar realm we live upon, and the moon is one of the biggest mysteries, and hopefully I've helped explain why we see the moon as we see it. The craters are real and physical, but they're all shallow, they're all round. Some look like big explosions, which would what you'd be expecting if it's a big ball of magma, blown into a big bubble that becomes diamagnetic. How much time have I got left? I've got 5 more minutes. All right. So it's diamagnetic, and it may be filled with helium. I'm pretty sure it's filled with helium. It could be hydrogen, but I don't think hydrogen, because it's too flammable. So when it was made, the hydrogen would have blown it up into a big ball. But helium is protectant from fire. That's why they use it in welding. Same as argon. So it's probably filled with helium, and that's what puts it up there. So diamagnetic force is a repellent force. It's like when you put the two like poles of magnets together, they repel each other. Well, diamagnetism isn't anywhere near as strong as that, but it's still a mild, weak force, and everything is diamagnetic. It's just that the magnetic force is often stronger. Well, if there is a magnetic force, it is much, much stronger. So if you've got a metal and a magnet, they are diamagnetic towards one another, but they're also magnetic, which means the magnet will make them stick hard and stay stuck unless you pull them apart with force. But diamagnetism is like two like poles trying to push together, but they won't go. It's similar to that. So everything is diamagnetic. Mass and density and everything else overrides it. So we don't even notice diamagnetic forces in general. But the moon, being so massive, as I imagine it to be 70 miles wide, since that's the size of the shadow it casts during a solar eclipse on the Earth, that would tend to suggest that's how big it is. Now, that might not necessarily be the case. It may be much smaller because, as you know, when you do shadow puppets on the wall, the shadow on the wall can appear a lot bigger depending on how close your hand is to the light source. So the moon, whatever size it may be, as it wafts around, similar to the sun, it's on a more elliptical sort of orbit. So it's a bit like when you see those old images of how atoms work. It's doing loop and then loop and then loop, and that's how the months go throughout the year. The force that holds the moon aloft, diamagnetism, also has a downward pressure on the Earth. So the Earth is like the magnet, the moon being the diamagnet. I don't know the correct words to explain this, to be honest, but all I know is it's a diamagnetic force. The force of the moon then pushing down is sufficient to create a big well depressing across the saltwater oceans, which are teeming with electrolytes. So it's very important. It only works on saltwater bodies and doesn't affect freshwater bodies, depending on how much saline content they got. Salt is electrolytes. Oceans are very salty. If you wanted to make fresh water into salt water, take 10 litres of water and add 30 teaspoons of salt, then you've got salt water. That's how much salt you need to add. That's how salty the oceans are. So the moon depresses on it, and as it wafts around, it is pushing the ocean ahead of it. So towards the east coast, it is pushing the tide ahead, but also behind it is having a lesser effect, also pushing the oceans away. So that's why you get the lesser of your high tides back the other way. Then as it reaches the coast, by that stage, it's pushing directly down, and that's when you've actually got the low tide. So you will see high tide at moonrise, and you'll see low tide when moon is overhead. Completely opposite from the stupid nonsense to think that gravity of the moon pulls the oceans, because you've only got one moon. You can't have 2 tides per day on a spinning ball. It just doesn't work. That's how it works on the flat Earth. Then the moon passes overhead across the continent, drives the next tide as it approaches, so they're getting a low tide, and then as it passes over again, it pushes the tides back again, and then they'll get a high tide. And that is why there are 2 high and 2 low tides every 24 hours and 50 minutes in phase with the moon. The sun has got very little to do with it. The tides can only work on the stationary planar Earth. They cannot work on the globe, because the globe has all the gravity pulling everything towards the center of the globe, which means all the oceans. And then you've got a moon 238,000 miles away, pulling the oceans that direction. The backside of the Earth cannot have a high tide, because you've got the Earth's gravity and the moon's gravity pulling together. It's impossible to have a secondary high tide every 24-hour, 50-minute period on the globe. But it can work on the stationary planar Earth, with the moon being a repellent force, just a gentle repellent force. It's not a strong one. It only pushes the oceans by a couple of meters, and it will be delayed in various places, and depending how far from the equator or the moon's path that it's on at that particular time, there's all sorts of delays and topographical bloody interferences, and you name it, bays, inlets, local rain, all sorts of things will affect the tides. But in general, if you follow that rule of a diamagnetic repulsion force of the moon, and then think of the delayed effects that will have on different places, you will see that is the cause for tides. I'm Ross Thatcher, Iron Horse. Thanks for listening.